Hello AC circuit students. This is the second in our video demos with looking at magnitude and phase of voltage drops over a resistor and a capacitor in series. So we're looking at an RC series circuit, and rather than having a square wave voltage, something that we might have used to find the time constant of the circuit, we're imposing this time a sinusoidal voltage. And so now we can look at phase and magnitude relationships of total circuit voltage versus voltage drop over each component. So in our first video, we used SMath and we applied all of our Ohm's law calculations using polar mathematics. So we used magnitude and angle or real and imaginary components, used our trig relationships. And we developed expressions for the voltage drop over the capacitor, voltage drop over the resistor, and then looked at the voltage drop over the whole circuit and equated that to whatever our source voltage was. So we're going to quick draw that SMath spreadsheet, and I'm not showing it, but I have it off on my second screen, and I'm going to refer to it. And I'm not using a video to show, but I have built a series RC circuit on my protoboard, and I'm showing you the unpowered view of my Picoscope. And I have my arbitrary waveform generator, my AWG from my Picoscope, powering the whole circuit. So I have that through my kind of my power rail on my protoboard. And then I am measuring on channel A into my Picoscope, showing that on my oscilloscope. I'm looking at the total circuit voltage. So that would be equivalent to the source voltage that we saw on the SMath spreadsheet calculation sheet that we developed. And then on channel B, I'm looking at the voltage drop just over the capacitor. So I'm measuring between ground and the capacitor, making sure that I'm not creating any kind of ground loops and altering my circuit. So the first thing I'm going to do is I'm going to turn on my signal, and showing you here, I'm not using a square wave, I'm using a sinusoidal signal. I'm going to start with 1 kilohertz. And I'm going to ask my AWG to please give me a 1 volt amplitude signal. So that would be 2 volts peak to peak. Now it probably won't actually manage to give that to me, because we know that the Picoscope is a very low current capability source. So it's what would be known as a very non-stiff source. So the voltage is going to sag as we try to flow current through our circuit, even though it's a reasonably high impedance circuit. So I'm going to turn on my voltage source, and surprise, surprise, I'm not seeing anything happen. Well, that's because I'm not looking at either of my channels. You can see over here, channel A and B are both off. So I'm going to turn my channel A on and take a look at what the total circuit's doing. And I've turned it on, and the oscilloscope is having a hard time not knowing where to stop redrawing my waveform. And in order to solve that problem, I'm going down to trigger and asking for an auto trigger that says only start redrawing the waveform if it changes from this point. And so kind of by default, our Picoscope software likes to put the default waveform kind of right in the middle where the waveform crosses a 0 point. Here's something, now let's look at our waveform a little bit. So first thing we're going to notice is the trigger, which is kind of indicating the 0 point, the midpoint between maximum and minimum. It doesn't quite correspond to the 0 over here. We do have a little bit of a DC offset, and so that's a bit of an error in our signal that we're not going to go crazy over, but we're going to stay aware and see how it compares to our other signals, because that might change where we have to draw our 0 lines when we go to measure our phase angles between signals. We're seeing a little bit of noise, so if we're looking at at trying to find maxima and minima, that might be a little bit of an issue. So one thing we can do to remedy that, we can go over and click on the down arrow of our channel A, and we can say, average more than 8 bits. So actually, here's what 8 bits looks like. We were already averaging. So if we said take a few more data points and then average them and display it, that's really what we're doing. So that's about all we want to do, because if we ask it to average too much, we can actually change the signal that we're displaying. Okay, so sinusoidal signal, a little bit of a DC offset, not quite sure where that's coming from, but it is pretty small. So the next thing we want to do is say, well, what is the actual magnitude of this signal? What is the amplitude that we're getting? We have 2 ways we can determine that. We can either use our pull downs and read off the value that they give us, and we are allotted 2 for each y-axis. So we can already see that there's that DC offset. So we've got a maximum of 9.34 and a minimum of negative 967. So our midpoint is instead of at 0 volts, it's at maybe negative 15. Very small, but still a little bit. So if we want to not have to use those, another way to determine our magnitude is to go to a measurement, and it asks, is a measurement tool. So this is some automation here. Which channel? Well, channel A, it's the only one we're displaying. It defaults to our RMS magnitude, which we really don't want here. Let's ask it for what it thinks the maximum is, and it displays it down here, and it's going to base it on a 20 count capture, so that gives us a bit of a time averaging. So it thinks that that we have a maximum value that corresponds to the tops of the sine wave of about 939.2 millivolts, and that's being displayed down here. It's kind of small, but it's intended to be kind of out of the way. So let's go ahead and add another measurement, also on channel A, and let's capture the minimum. And as we saw when we tried to do this with our slider hand measurements, we're getting something that's more negative than we had the positive going. Excuse me. And so we have a little bit of an offset. But we can still use those 2 numbers to calculate our amplitude. So what we can do is just find basically the average of those 2 numbers. So we have 939.2 and 971.3 plus 2 divide. So the average amplitude of our signal is just a little bit less than 1 volts. It's about 0.955. So over on I have my SMath spreadsheet up, so I'm putting that in for the voltage source magnitude, and I'm going to leave the angle at 0. I'm also going to remember that I have about a 15 millivolt, negative 15 millivolt offset. So I'm going to use that when I draw my zeros when I start looking at angles. So this is my source. So the voltage drop over my capacitor and the voltage drop over my resistor should add up to give this signal if I measure them both and combine them. Okay. So I'm currently measuring but not displaying the voltage drop over the capacitor. So let's go ahead and take a look at what that looks like. I'm going to take my channel B and I'm going to turn it on to auto. I'm not quite sure what the value is. I can look on my spreadsheet or my SMath sheet, but I'm going to let the Picoscope find it. If I click auto rather than deciding on a range, I don't get the out of range error, which is not necessarily so good for the scope. So I hit auto, and now we can see our channel B is being displayed. Nice waveform, not a lot of noise. I'm taking 9 bits and averaging, not the default 8, so that's giving me a little bit smoother curve. And let's see what scale we're on. So we're at plus or minus 500 millivolts. So again, I can use my slider bars to kind of estimate amplitude. So the top is around 447, and the bottom, I'm guessing, is going to be a little more negative than positive. So negative 481. So again, we have a little bit of a DC offset to the negative side with this signal as well. And we have a delta of, we can see here, of 928. And we're gonna use the measurement tool and let the computer determine our max and min, and then we'll go ahead and we'll calculate an amplitude. So this time I want channel B, I want a maximum, okay, based on whole trace. So it's giving me 448.9 value. And the max min here are the maximum and minimum values that it finds over the whole trace. So now I'm gonna look for the average min value of my red waveform, my channel B, voltage drop over my capacitor, minimum, okay. So I'm getting negative 478.4, this number right here. So now I'm gonna calculate an amplitude, and then I will be able to compare that immediately to my calculated value on my SMath sheet. So I have 448.9, 478.5 plus 2 divides. So an average of magnitude of 400 and call it 64 millivolts, give or take. So I go back to my SMath sheet, which I'm not displaying, and I have calculated a value of 499.5. So there's definitely a little bit of a difference, but given that, remembering that the value of our capacitor is plus or minus 5%, that's probably within the error of my components. Speaking of which, you can't see this. I've entered it on my SMath sheet, but I am using a nominal 2.2 times 10 to the minus 8 farad capacitor. So that would be displayed on the front of the component as 22.3, meaning 22 times 10 to the third, all expressed in picofarads. So that's the same as 2.2 times 10 to the fourth times 10 to the minus 12, which gives you 10 to the minus 8. And my as measured value of my resistor that I'm using in series with that is actually 11.79 times 10 to the third ohms, or just a little bit less than 12 kiloohms. And I am currently, of course, imposing a 1 kilohertz signal. So that's if you have an SMath spreadsheet, if you want to put those values in, you can compare to what we're measuring. So we're in the ballpark in terms of the predicted magnitude of the voltage drop over the capacitor, but somewhat less. So that could be due to, again, to a little bit of a difference maybe in the component value, as well as other errors in the measurement, exactly how the computer is calling it. And as you can see, we've got some noise at the top, so there's some uncertainty in exactly what our amplitude is. Okay, let's think about our phase angle. So the first thing we're going to want to look at is we know that the voltage, the angle of the voltage drop over the capacitor is negative with reference to our 0 degree source reference. Our 0 degree source reference is actually represented by where our trigger point is, because the total circuit voltage by KVL has to equal the source voltage. So we can take this 0 point here that just so happens to be our trigger, which is kind of convenient, and say that's 0, that's the source, and we're saying that the voltage signal over the capacitor should be lagging. It's at negative 58 degrees versus the source, and we can see that that is indeed the case, because if this is a 0 time, then where our source, or our total circuit voltage, is crossing the 0, then the red curve representing the voltage drop over our capacitor doesn't get to that same point until somewhere around 179.6 seconds. So since it takes longer to reach the same point, it must have been behind or lagging, hence the negative degrees. So we're not accounting for the fact that we've got a little bit of a DC offset, and our zero crossings is a little bit harder to determine. We're just going to use basically the 0 point to indicate relative times when each of these, our curves, our blue curve and our red curve, hit a reference time. So I'm not gonna actually draw another line, but I am going to spread them out a little to make it easier to measure phase angle. So what I'm going to do is I'm going to look for the time when the red curve, maybe just a little shy of when it crosses 0 degrees. So so here's what we want to see, maybe just a little shy of it. Maybe, you know, put our little offset in, or capture part of it there. So I'm giving a horizontal line. So I'm looking at when does the red curve cross that dotted line that I've established, and it's, you know, it's somewhere in around here. So we've definitely got a little bit of measurement error. So we're looking at 175.2 microseconds. Okay, so how do we take 175.2 microseconds of lag and equate that to degrees, which we calculated on our SMath sheet? So we actually calculated negative 58.5 degrees. How does 175.2 microseconds compare? What we have to do is use the frequency of the signal that we've imposed and say, what fraction of one cycle is 175.2 microseconds? So for that, we would say, well, 1 kilohertz is 1,000 inverse seconds. So we would end up saying we have 0.001 seconds per cycle, or per complete time to have a complete waveform. So that means 0.001 or 1 millisecond would correspond to going from one point on the waveform all the way through and coming back to the other. And as you can see on our time signal, if this is 0, that same crossing point is corresponding to negative 0.1 milliseconds if you're looking at what I'm circling on the x-axis there. Okay, so basically all we have to do is take 175.2 microseconds, divide it by 1 millisecond, and we get the fraction of a cycle. Well, if a cycle is 360 degrees, we just multiply that fraction of a cycle that corresponds to the lag, the time lag, and we get a degree lag. Okay, so basically, as you'll notice, the time for one cycle, if you invert it, it actually gives the frequency. So all we really have to do is multiply 175.2 times 10 to the minus 6 times 1,000. We get 0.1752. We multiply that by 360. And we get about 63. We had calculated 58 as the magnitude of the angular difference between the capacitor voltage signal and the total circuit. We are a little bit off, but we are nonetheless in the ballpark. So, and we are, of course, we are lagging. So it's important we have our signs right. So we're gonna turn our signal off, and we're gonna make a few changes at this point. We could either at this point change components and look at the difference, and we could predict that by changing the values for R and C in our spreadsheet. But that would require doing something different with our circuit on our proto board. One of the easier ways to look at the relative differences between reactive impedance and real impedance is to just change the frequency. So what we had seen in our spreadsheet, or excuse me, our SMath sheet, our calculation sheet in our earlier video, now we used a different value for capacitance, but we noticed that 1,000 hertz, resulted in a fairly low reactive impedance with a smaller capacitor it's equating to something bigger, but it's still smaller than our real resistance. So let's go ahead and change the value of our, we're going to turn that off again. Let's change the value of our imposed frequency, and let's go to something very low or somewhat lower. Let's go down by an order of magnitude. Let's go to 100 hertz. Let me turn our signal back on, and we're seeing only part of our total circuit waveform. So we need to basically increase the number of seconds per division because there's a lot more seconds per cycle with this lower frequency. So now we have our a reasonable frequency, and we're going to take a look at our measurements. Again, we have about the same total amplitude, and this time we're our DC offset seems to be a little bit less. So we go between 975 and 1,000 millivolts. So this time we're imposing an amplitude of about 988 millivolts, or 0.988. So I'm going to change that in my predictions in my S-math sheet. I'm going to change numbers a little bit. So at this point, what we've done is we've increased the capacitive reactance. So the capacitor is now accounting for a much more significant fraction of the overall circuit impedance. So we would expect, first of all, because we've increased that, we haven't reduced the voltage drop, or we haven't reduced the magnitude of the resistor. So we would expect the total impedance to be higher, which is something we kind of saw with the higher amplitude of our total as measured signal. We're asking the Picoscope to give us 1 volt amplitude. With our higher frequency and therefore our lower capacitive reactance, we only got 955 millivolts. That's because our Picoscope was sagging. We were asking it for a little more current than it could give, and so it gave us less voltage. By reducing our frequency, we've increased the overall impedance of our circuit in the form of higher capacitive reactance and the same resistance, so the Picoscope is able to give us closer to what we asked for. So we've already, just with our as measured amplitude of our full circuit voltage signal, we were able to confirm that we have increased one of the two reactive components. And of course, given that they're in series, that's something we're really going to see. So let's go ahead and turn on our capacitance signal, and we're letting the Picoscope find where it is, and wow. Take a look at the scale. We have the same scale now. We're on auto, we're letting the Picoscope find the proper scale. And now the magnitude of the voltage drop over our capacitor is almost the same as the voltage drop over the resistor. These two curves are very close in magnitude, and we can look down at our numbers and see that we're within about 10 millivolts, in fact. And furthermore, if we kind of spread them out, go the other way. If we're to look at the phase angle between the two signals, again, we're still lagging, but not by very much. So now we have, and this is going to be very approximate, but we have 370.1 times 10 to the minus 6 at 100 hertz times 360 times. So about 13 degrees lagging is what I'm measuring. My calculation sheet predicted about 9 degrees lagging. A little bit of error, but again, we're in the ballpark and we're going in the right direction. So that is in fact exactly what we would have predicted as we went from a high frequency where, given the component values we had, the total circuit impedance of our series RC circuit was kind of being shared by the resistor and the capacitor. As we reduced the frequency, the reactance of the capacitor increased, so it's providing the main impedance to current flow. So we could, as maybe a test, we could go to a higher frequency, which can be a little problematic sometimes for the Picoscope, but we're going to try imposing a little bit higher one. Let's go to 5K and see what we get. And I'm displaying both signals at the same time. And we have a high frequency, so there's very little time per cycle, so we want less time per division to spread them out. And we can see now we've gone the other direction. The Picoscope has picked a 200 millivolt full scale, and I'm kind of circling it up in the upper right to display our capacitor voltage drop, and that's because it's a really low number now. So we basically have kind of a peak to peak of something around 200 millivolts, maybe a little over 200, or an amplitude of about 100 millivolts, as opposed to an amplitude of about 940, give or take, for our total circuit. So now the capacitor isn't providing a whole lot of impedance to current flow, which we wouldn't expect for the higher frequency. And we can also take a look at the effect on our phase angle. We would expect the lagging to have increased. Now our capacitor is not nearly as superimposed, so we can look at our 51.7 microseconds, 5,000 times, 360 times. So at this point we're looking at practically 90 degrees, something quite high, almost completely out of phase. And so I'm going to update my SMath sheet, and my SMath sheet predicts negative 83 degree angle for my capacitor voltage drop. So that's almost 90 degrees. So we're almost a quarter wavelength out of phase, and we would probably measure that easier if we were to account for the fact that we have a little DC offset, so probably we ought to be over here. So our measurements, if I move over there, I would have 49.8 times 10 to the minus 6, 5,000 times, 360 times, that's 89, negative 89. So again, I'm within a less than 10% error with my measurements. So basically, within the error of my component values and the error associated with my measurements, I'm seeing that my component values, the voltage drop behavior is falling into line with my calculations. That said, I am definitely seeing some differences. I'm going to turn off my voltage signal. So I am seeing, for instance, we're seeing a little DC offset. That doesn't have a real obvious explanation other than this is something we'll pick up in semiconductors. If you study that, many interfaces in a circuit can act a bit like a diode. So there could be something that is accumulating charge and producing that shift. And that could be any interface in the circuit or the measurement circuit itself. Also, we've got some error in exactly where we're putting our measurement lines. It's really hard to call it exactly, but the fact that we're within 5 or 10%, when you combine measurement error and component error, we can conclude that our calculations and our measurements are well correlated. Okay, last thing that we want to show, and we'll go back to our 1K because that gave us a fairly good split in impedance between the resistor and capacitor. We're going to go ahead and look at the effect of, the fun of visualizing the voltage drop over the resistor. I've put my capacitor in my physical circuit closest to ground. And as we all know, I can't just use my alligator clip from my probe scope to measure over the resistor, or I'll literally cut the capacitor out of the circuit. So one of the ways that I can measure the voltage drop over the resistor, if I wanted to look at it by itself, is again to use Kirchhoff's voltage law with the oscilloscope. And remember that the voltage drop over the resistor is the difference between the total circuit voltage and the voltage drop over the capacitor. They have to add up. So I can come over to Tools and look at Math Channels, and I can create another display that is calculated by my scope software that is the difference between the two signals. And a lot of digital benchtop scopes have this function too. So I want to look at my total circuit voltage, which is my channel A in blue, minus the voltage drop over my capacitor, which is in red. So I'm going to look at A minus B right here. And what I'm going to get when I hit OK is a display, a trace in this burgundy that represents the difference in the two signals. There we go. And it's going to have its own scale. So it's actually on the same scale as the total circuit voltage. So if I look over at the scale, the red scale on the right that's representing my capacitor, I can see that, that more of the voltage is being dropped over my resistor. And if I take a look at the phase angle, I can see that compared to the capacitor, the voltage drop over my resistor is actually going the other way in this case. So, the difference is it's actually leading rather than lagging. Which is, again, something that I would have predicted from my S-Math sheet. So I could go through the same measurements. I can blow this up a little bit to make it easier. Look at this trace. So now I'm looking at where does the kind of the purple curve cross its 0 point, and then I can look up and see 76.49 microseconds. I'm at a frequency of 1 kilohertz, 1,000 times, so I'm looking at 0.0765 fraction of a cycle. One cycle is 360 degrees, 360 times. So I just measured about a 28-degree leading angle of the voltage drop over the resistor versus the source or total circuit. I calculated a 32 degree on my S-Math spreadsheet. So again, there's some error, but I'm in the ballpark and I'm in the right direction. So just to show, again, here's my source, the blue signal where it's crossing the 0, corresponding to this little yellow triangle where our trigger indicator is, or our trigger point, really. If I look at my capacitor, it's crossing that same point in its waveform at almost 175 microseconds, but the resistor is crossing it at what effectively negative 75 microseconds. So resistor voltage drop signal is leading, capacitor voltage drop signal is lagging, reference to the blue total voltage source. So we can, if we want, we can do some adjustment of our frequency, small adjustments there where I increased it, and as I did, we saw the resistor signal will start decreasing, the capacitor will increase, and then finally probably scale up. Oh, excuse me, go the other way. Scaling up to 1 volt. It's going in the wrong direction. And likewise, getting smaller in the case of the resistor. Finally, eventually, as we go towards something like DC, we're going to have to change our y-axis As we go to something very low, we're seeing very little voltage drop over the resistor because most of it is being dropped over the capacitor. So you're seeing all three together. Total circuit in the blue, capacitor in the red, and resistor by difference in the purple. And that's pretty much it for things to measure in this simple RC circuit. We obviously could have reversed the physical position of our resistor and capacitor, in which case the red curve would have been measuring directly the voltage drop over the resistor, and then we could have found the capacitor by difference. So again, conclusion, our measurements were not dead on with our calculations, but they were well correlated. We did have some error in measurement. We had some offset, a DC offset that was a little hard to explain, but it was, again, very small compared to the magnitude of the other signals. And so we could take a look and say that we were probably within about 5% or 10% at most difference from our calculations. A final word about difference in as measured signals to as calculated. Something to remember about our reactance, our frequency and capacitance and inductance relationships with reactance, our X sub C's and our X sub L's. Those assume ideal behavior. Those assume that our component is behaving as nothing more than a capacitor or an inductor, if we had looked at inductance. And we know the real components always have a certain amount of resistance, and that the actual, again, we have a wide range in the actual capacitance, and inductors tend to be the less ideal. So we would never expect our calculations using those ideal expressions to necessarily exactly match what we measure, but we should be close. And as we know, we would expect to be closer with an RC circuit than an RL, because our capacitors are more ideal than our inductors. So that is it for our demo, and hope you enjoyed, and feel free to make your own sheets and do your own comparisons with your as built and as calculated.